Hello there, and welcome to the Sleepy Scientist, your quiet little corner of the cosmos, where curiosity meets calm, and science gently rocks you to sleep. If you're here tonight, it probably means your mind needs a little peace, a gentle story to soften the edges of the day. Maybe it's been a long one. Maybe the thoughts just won't quiet down. Or maybe you're simply in the mood to drift, to let go of the noise, and float a little while. Whatever brought you here, I'm glad it did. Now, before we start tonight's voyage, I'd love to know, where are you listening from? And what time is it where you are? I'm always amazed by how many of us are quietly connecting across time zones and continents. Someone's in London, brushing their teeth. Someone's in Vancouver, watching the sunset. Someone's in Tokyo, already wrapped up in dreams. Different skies, same stars. That always feels comforting somehow. And if you enjoy these quiet little trips through the universe, feel free to give this video a gentle like, or maybe subscribe. It's not about the numbers here, it's more like leaving a candle in the window, so that others who need a little wonder in the dark might find their way. Okay. Let's get settled. Let your shoulders drop, just a bit. Unclench your jaw, we all hold so much tension there without realizing. Take a slow breath in, and a longer one out. No rush. The stars will wait. Tonight, we're going on a journey, not through one place, but through time itself. We're going to explore how galaxies, those great glowing cities of stars, came to be. We'll start at the very beginning, when there wasn't even a single star to shine. Just darkness, silence, potential. Now I promise, this won't be a science lecture. You won't need a PhD in physics to follow along. This is a story, a quiet, wandering kind of story. We'll talk about gravity and dust, about ancient light and invisible threads. But we'll do it slowly, gently. Like tracing your fingers over the night sky. And if you fall asleep partway through, that's okay. Honestly, that's kind of the goal. There's no test at the end. No right answers. Just the comfort of knowing that the universe is vast, ancient, and full of quiet beauty, and somehow, you are part of it. Sometimes we forget how incredible that is. We walk through our days answering emails, folding laundry, paying bills, and all the while, we're spinning on a planet that orbits a star that lives inside a galaxy that's just one of trillions. Trillions. And every one of those galaxies has its own story, full of stars that lived and died long before the Earth was ever born. Tonight, we're going to trace those beginnings. How everything came from almost nothing. How chaos turned into order. How the dark learned to shine. But for now, all you have to do is listen. You can close your eyes, or stare at the ceiling. You can be in bed, on a couch, on a plane. Wherever you are, you're in exactly the right place. Because right now, we're standing at the threshold. On the edge of time itself. The beginning of everything is just around the corner, and you're already here to see it. So, settle in. Let's begin. Let's begin at the beginning, not just far away in time, but at the very edge of it. Before galaxies, before stars, before atoms, before anything we can truly imagine. There was no sky to look up at. No space to move through. No time to wait for. There was something. But we don't really have a word for it. And even if we did, it wouldn't quite capture what it was, because it wasn't a thing, exactly. It wasn't a dot floating in space. It was space. Or, the potential for space. A singularity, they say, where everything we now know, everything we've ever seen, everything we are, was compressed into a point smaller than a grain of sand. Not sitting somewhere. Not glowing. Not spinning. Just, being. And then, suddenly, wonderfully, mysteriously, that point began to expand. This is the moment we call the Big Bang. But the name is a little misleading. It wasn't a bang the way we normally think of bangs. There was no sound, no fireball, no explosion echoing through a dark and quiet sky. There was no sky. There was no echo. There was no out there for it to echo into. What really happened was more like a blooming, a swelling of space itself. A moment of sudden, overwhelming expansion. Everything began to stretch, not into space, but as space. Imagine a balloon inflating, not from the mouth of a person, but from every point at once. Every atom of rubber expanding outward together, creating more surface with every passing instant. That's what the Big Bang was. Not a blast, but a beginning. And it happened fast. Unthinkably fast. In the first trillionth of a second, a span of time so short we have no real intuition for it, the universe grew from something unimaginably small to something, still tiny, but vastly larger than before. That early phase is called inflation, and it was nothing short of astonishing. During inflation, space didn't just expand. It accelerated, blowing outward faster than the speed of light. That's hard to wrap our heads around, but here's the thing, the speed of light is a limit for things moving through space. But space itself? Space can stretch as quickly as it likes. And so it did. Inside that newly stretching space was chaos. Not the kind of chaos we deal with on a Monday morning. No traffic jams or tangled cables or emails from 3 different time zones. This was fundamental chaos, a roiling broth of energy, temperature, and pure possibility. There were no atoms. No protons or neutrons. Not even the tiniest building blocks of matter. Just energy. And from that energy, tiny particles began to emerge, quarks, leptons, bosons, blinking in and out of existence in fractions of a second. It's hard to describe what this early universe was like, because it was unlike anything we've ever seen. The forces of nature, gravity, electromagnetism, the strong and weak nuclear forces, hadn't even separated yet. It was as though reality itself was still figuring out how to behave. If you could somehow stand there and watch, which you couldn't, because nothing existed that could stand or see or survive, but if you could, it would have been blinding. Hotter than the core of a star, denser than anything you can imagine. A storm of radiation and particles, crashing into each other, transforming, annihilating, being born again. And yet, in the midst of all that madness, something was already beginning to take shape. Because one force, one ancient presence, was already at work. Gravity. Not loud. Not dramatic. But constant. Quiet. Relentless. Gravity doesn't rush. It doesn't yell. It just pulls, always, everywhere. Even then, in those first flickering moments of reality, gravity was noticing small differences, tiny, microscopic ripples in the density of matter and energy. Imperfections. Flaws. Wrinkles. And it began to pull. Those small wrinkles, those little oops moments in an otherwise smooth universe, they were everything. Because gravity doesn't forget. It remembers where there's just a little more of something. And over time, it pulls a little more toward it. And then more. And more. Until you have stars, planets, galaxies. But that's getting ahead of ourselves. Right now, the universe is still a baby. A flashing, furious, unrecognizable thing. But it's becoming. The laws of physics are starting to separate out. Particles are becoming more stable. Quarks are clumping into protons and neutrons. The energy is still intense, but the universe is cooling, rapidly, like a hot pan dipped into cold water. And the beautiful part? This expansion, the original unfolding of the cosmos, never stopped. It's still happening now. Right now. As you're listening. As you breathe. As the Earth turns and the stars will overhead, space is still stretching, pushing galaxies apart, making room. So no, the Big Bang wasn't a bang. It was a breath. The first breath. Soft. Vast. Infinite. And from that breath, everything we know, everything we are, would follow. In the beginning, there was no shape, no light, no sky, just the aftermath of a moment so fast, so furious, and so fundamental, we still struggle to describe it. Right after the Big Bang, the universe wasn't made of stars or galaxies or even atoms. It was a thick, swirling soup of raw energy, a place where nothing familiar had yet come into being. Everything we now see, touch, or even imagine was locked inside a seething storm of particles, flickering in and out of existence at unimaginable speeds. It was hotter than any star that's ever burned, denser than the core of any black hole, and expanding faster than light itself. Time had just begun, and space was still deciding how big it wanted to be. Inside this newborn cosmos, chaos reigned. The first entities to appear were the smallest imaginable: quarks, gluons, electrons, and photons. Quarks darted wildly, free and unattached, constantly nudging and bouncing off each other. Gluons, like tiny cosmic messengers, raced between them, binding them for fleeting moments before they broke apart again. Photons, the particles of light, were already present, but not in the way we know them now. The universe was so dense, so tightly packed with particles, that photons couldn't travel more than a tiny fraction of a millimeter without crashing into something. They ricocheted endlessly, trapped in a pinball machine of matter and heat. There was no glow, no visible light, no radiance, only the raw presence of energy and motion, intense and wild. At this point, the 4 fundamental forces of nature were still merging, tangled in a single knot of raw interaction. But as the universe expanded and cooled, they began to unravel, to take on their individual forms. Gravity became the quiet sculptor, pulling matter gently but relentlessly. The strong nuclear force stepped in to glue quarks together, setting the stage for the birth of protons and neutrons. Electromagnetism began laying the groundwork for light and electricity, while the weak nuclear force influenced the balance and transformation of particles behind the scenes. These forces, still invisible, still mysterious, became the rules of the game, the invisible grammar of the universe. Then, something extraordinary happened. As the temperature dropped just a little more, quarks began to settle into stable formations, groups of 3 quarks locked together, forming the first protons and neutrons. For the first time, the universe had made something that would last. Not for a fraction of a second, not for a blink, but something durable, something solid. These tiny particles were the seeds of everything that would come. Electrons also began to appear in greater numbers, flitting about like tiny dancers, still too fast and too hot to settle down into anything like an atom. But the building blocks were all on the stage now, ready for their roles in the great cosmic story. And all the while, the universe kept growing. Not in a straight line, but in every direction at once, swelling like bread dough rising in an oven, except the oven had no walls, and the dough was made of time, space, and energy. As it expanded, it cooled. As it cooled, it calmed. The collisions became less frantic. The flashes of pure radiation grew less frequent. It was still hot, unimaginably hot, but compared to the first moments, it was beginning to feel, in a strange way, a little more familiar. Still no stars. Still no atoms. But gravity was watching. Waiting. Gathering. Wherever there was the tiniest bit more mass in one place than another, gravity leaned in, nudging things together, remembering where the universe was slightly uneven. These differences, tiny, microscopic imperfections in the smoothness of space, would one day grow into galaxies. But for now, they were whispers. Small ripples in a vast sea of heat and light. And yet, even at this early stage, the direction was clear. The universe was moving from chaos toward structure. From pure energy to particles. From nothing we can name to the ingredients of everything we know. The story hadn't yet become visible, but the first words had been written. The ink was hot plasma, the paper was spacetime, and the author was a set of physical laws we're still trying to understand. In this chaotic silence, the universe was still too young to shine. But it was learning how. And like a breath drawn in before the first note of music, it was preparing to light up the darkness. As the universe continued to expand and cool, the chaos began to soften. What was once a furious storm of particles and energy started to calm, just slightly, like a fire that's still burning, but no longer wild. The temperature, while still intense by any human standard, was dropping rapidly. And with that drop, something beautiful was about to happen. Particles were going to start sticking together, not just momentarily, but in ways that would last. This was the next step in the grand unfolding, the birth of the very first elements. Up to this point, we had protons and neutrons, heavy particles, born from quarks, wandering the cosmos in high-speed chaos. We also had electrons, smaller and lighter, zipping around like gnats on a summer night. But nothing was structured yet. These particles weren't locked into anything that could build the world. They were ingredients, but there was no recipe. That was about to change. Roughly 1 second after the Big Bang, the conditions were just right for protons and neutrons to start bonding. When a neutron and a proton get close enough and the temperature isn't too high, they can fuse to form something new, a deuteron, the simplest form of a nucleus. Add another proton, and you get helium. Add a few more steps, and for the first time, the universe begins building real atoms. This process is called Big Bang nucleosynthesis. It's the cosmic equivalent of snapping Lego bricks together for the first time. And what it produced, more than anything else, was hydrogen, lots and lots of hydrogen. About 75% of the normal matter in the universe became hydrogen. The other 25% became helium. A trace amount, just the tiniest sliver, became lithium. And that was it. No oxygen. No carbon. No iron. None of the heavier elements we now think of as essential for life. Those would have to wait for stars, which hadn't yet formed. But in this early moment, the universe was already laying the groundwork. Hydrogen and helium are simple, but they are powerful. With just those two elements, the stars could be born. And with stars, everything else could follow. The timing was delicate. If the universe had cooled too slowly, all the neutrons might have decayed before they could fuse. If it had cooled too fast, there might not have been enough collisions to form helium. But it was, against all odds, just right. In a span of about 20 minutes, no more than the time it takes to make a pot of tea, the universe completed the vast majority of the nuclear fusion it would ever do on its own. After that, the temperature dropped too low for fusion to continue. The era of element making, at least for now, was over. What followed was a pause. Not an end, but a waiting period. The hydrogen and helium nuclei were out there, drifting through the ever-expanding cosmos, but they couldn't form full atoms just yet. The universe was still too hot for electrons to settle into orbit. Any time an electron tried to latch onto a nucleus, it was almost immediately knocked away by a high-energy photon. It was like trying to light a candle in the middle of a windstorm, the flame just couldn't take hold. But with time, the universe cooled further. It kept stretching, kept expanding, and slowly, steadily, the photons lost energy. They stopped bullying the electrons so fiercely. And finally, around 380,000 years after the Big Bang, the temperature dropped low enough that electrons could settle in, and stay. This was a turning point. For the first time, neutral atoms formed, real hydrogen atoms, real helium atoms, complete and stable. The universe, which had been opaque up until this moment, suddenly became transparent. Light, which had been bouncing endlessly from one particle to the next, was finally free to travel. That light is still traveling today. We call it the cosmic microwave background, the oldest light in the universe, a whisper from the past that fills the sky like an invisible fog. It is not bright. It is not loud. But it is everywhere, and it carries the memory of this quiet transformation. So now the universe had its first materials. Hydrogen and helium, not much on their own, perhaps, but in the hands of gravity, they were pure magic. These elements would drift, gather, and eventually collapse into the first stars. And in those stars, the heavier elements, carbon, oxygen, iron, and beyond, would be forged. But for now, the universe was still simple, still sparse. It was dark. It was quiet. But it was ready. The ingredients were in place. The stage was set. And the lights, the stars, would come soon. Now that atoms had formed, the universe was, for the first time, calm. It was also, quite literally, dark. Not poetic darkness, not stargazing darkness, but complete, absolute, infinite black. The photons that had once bounced around endlessly were now free, yes, but they were mostly low-energy microwaves, stretched out by the expanding universe. There were no stars yet to shine, no galaxies to glow, no planets to reflect light. Just hydrogen and helium atoms drifting in silence, scattered across a cosmos that was expanding more and more with every passing moment. It was a peaceful kind of emptiness, but one filled with hidden potential. If you could somehow float through this time, and let's imagine you could, you wouldn't see anything. There'd be no shapes, no shadows, no points of light on the horizon. Just a cool, invisible mist of gas, spread thinly across space. But even though it looked empty, it wasn't. It was full of quiet tension. Beneath the silence, something important was starting to happen. During the earlier inflationary period, that rapid, early swelling of space, tiny imperfections were stretched across the universe. Not visible flaws, but slight differences in density, like soft ripples in an otherwise still pond. Some regions of the gas were just a tiny bit denser than others. Not by much, maybe 1 part in 100,000, but enough for gravity to notice. And gravity, as always, remembered. Over time, these tiny overdensities began to grow. The denser regions pulled in more gas. The gas added weight. The weight attracted more gas. Slowly, gently, the universe began to shape itself, not with a bang or a flash, but with a whisper. Clouds of hydrogen and helium began to gather. Not in one place, but all across the cosmos, like dew forming on a spiderweb you can't quite see. These clouds were invisible, silent, and for the most part undetectable to anything that might have watched from the outside, but they were the seeds of galaxies. They were the wombs of stars yet to be born. This era is known as the Cosmic Dark Ages. It lasted hundreds of millions of years. And despite the name, it wasn't menacing. There were no monsters, no battles, no evil lurking in the void. Just the universe, waiting. Gravity worked slowly. It didn't rush. The gas clouds cooled. They thickened. They drifted. Occasionally, they bumped into one another and merged, but there was still no light, no energy bursts, no signs of life. In human terms, it would have felt like an eternity. But in cosmic terms, it was just a pause, a deep inhale before the first stars flared into existence. Still, if we could map this invisible moment, we begin to see the shape of something breathtaking. The universe wasn't organizing randomly. It was following patterns laid down during inflation. Over time, those patterns grew into filaments and knots, vast strands of dark matter and gas, stretching across the cosmos. This is what we now call the cosmic web, an enormous three-dimensional structure where galaxies would eventually cluster along the intersections and threads. It's hard to picture without seeing it, but think of a sponge, or a lacework of spider silk, stretching across space, with most of the matter clinging to the threads, and huge voids, dark, quiet nothingness, in between. At the center of it all was something we still don't fully understand: dark matter. It doesn't emit light. It doesn't interact with regular matter in the usual ways. But it has gravity, and lots of it. And that gravity began tugging on the hydrogen and helium gas, pulling it along, guiding it into place. Without dark matter, the universe might have stayed in a fog forever, cold, quiet, and unstructured. But thanks to this invisible scaffolding, matter began to collect and organize, forming the blueprints for what would later become galaxies. Not galaxies themselves, not yet. Just the shadows, the frameworks, the quiet outlines. And so, during this dark age, the universe wasn't still, not really. Beneath the silence, a slow, deliberate transformation was unfolding. The atoms were in place. The web was forming. Gravity was knitting together the first meaningful clumps of matter. And somewhere, in one of those invisible clouds, something extraordinary was getting ready to happen. The darkness would not last forever. In time, light would return, not the diffuse glow of scattered photons, but real light. Stellar light. Light born from nuclear fire. The first stars were coming. The wait was nearly over. And the universe, once formless and void, was about to sparkle. And then, somewhere deep within one of those silent, invisible clouds of hydrogen and helium, gravity tightened its grip. Slowly, patiently, it pulled the gas inward, compressing it until the pressure at the center began to rise. Temperature followed. At first, it was a whisper of warmth. Then, a slow boil. Then, fire. Not the kind of fire you see in a candle flame, but the kind that burns at millions of degrees, hot enough to break atoms apart and fuse them together into something new. In that single moment, unceremonious, unnoticed, and deeply quiet, the first star was born. It didn't explode into existence. It didn't scream. It simply turned on. A single point of light in a universe that had been dark for hundreds of millions of years. This was no ordinary star. These were what we now call population 3 stars, the very first generation of stars the universe had ever created. They were unlike anything that exists today. Massive, unstable, and incredibly hot, they formed from pristine material, pure hydrogen, helium, and just the tiniest trace of lithium. There were no heavier elements, no carbon or oxygen or iron. That purity made them burn faster and hotter than later stars. Some of them may have been hundreds of times the mass of our sun. Their lives were short, just a few million years, and they ended violently, in brilliant supernovae or by collapsing directly into black holes. But in those few moments of cosmic time, they changed everything. These first stars began to flood their surroundings with light. Ultraviolet radiation streamed out into the darkness, striking nearby hydrogen atoms and ripping them apart. This process is called cosmic reionization, a dramatic, peaceful transformation where the fog of neutral gas that had filled the universe for so long was gradually ionized and made transparent again. It was as though the shutters of the cosmos had been opened, letting in the light. What had been a cold, dark ocean of gas was now slowly glowing, not uniformly, but in patches, like campfires igniting across a vast plain. One by one, these newborn stars pushed back the darkness, revealing the shape and structure of the universe as it truly was. We'll never see those first stars directly. They were too far, too brief, and too faint to leave their light for us to catch. But their fingerprints are everywhere. They seeded the cosmos with the first heavy elements, the raw materials needed to build planets, oceans, and life. They carved out the first glowing bubbles in the hydrogen fog. They set the stage for galaxies to form. In a very real way, they were the universe's first artists, sketching the outlines of structure and complexity on the blank canvas of space. But these early stars didn't shine alone. They were often born in clusters, small, scattered gatherings of light, not yet the grand swirling galaxies we see today, but something smaller. Proto-galaxies, perhaps. Cosmic villages, bound loosely by gravity, trying to figure out what it means to be a city. As these stars lived and died, they changed the gas around them. Their explosions enriched the surrounding clouds with heavier elements. These enriched clouds cooled more efficiently, collapsed faster, and formed stars more easily. A second generation of stars emerged, population 2 stars, a bit smaller, a bit longer-lived, already more familiar. These stars marked the beginning of a cycle: birth, shine, death, renewal, a cosmic rhythm that would continue for billions of years. And yet, even as the stars ignited and the darkness lifted, questions remained. How did those tiny ripples in density, those faint imperfections from inflation, give rise to such vast and luminous structures? Why did some regions of space become bustling cities of stars while others remained empty and quiet? The answers lie not just in light, but in the patterns of that light, in the subtle traces left in the cosmic microwave background, in the chemical signatures buried within ancient stars, and in the faint, scattered glows captured by our deepest telescopes. These clues let us piece together the childhood of the universe, like archaeologists reconstructing a forgotten city from broken pottery and half-buried stones. Today, with observatories like the James Webb Space Telescope, we are finally starting to see the first galaxies take shape. What we see are not neat spirals or glowing ellipticals, but chaotic clumps, small, irregular islands of stars, glowing faintly in a sea of ancient darkness. These are the nurseries of light, the first drafts of structure, the echoes of the moment when the universe truly began to shine. And the light from those stars, the light that first ended the dark ages, has traveled across billions of years and unthinkable distances to land, softly, now, right here, in your mind. After the first stars were born and their light began to pierce the fog of the early universe, everything changed, but not all at once. The darkness didn't vanish overnight. It faded slowly, unevenly, like a sunrise that stretches across a landscape too vast to comprehend. Across this newly illuminated cosmos, the first stars shone in small, scattered groups. These weren't the elegant galaxies we imagine when we look up at telescope photos. These were fragile clusters, loose gatherings of stars held together more by suggestion than by certainty. There were no clear shapes yet, no spirals or glowing cores. Just small, glowing points of light, spread thin across space like lanterns lost in a deep forest. But even in their fragility, they represented something profound: the universe had turned a corner. It had gone from darkness to light, from gas to structure, and it was just getting started. These scattered stars did not float aimlessly. Gravity, quiet, invisible, and persistent, was always at work. Wherever a few stars were gathered, gravity was pulling them closer, drawing in more matter, attracting more stars. Slowly, gently, these clusters began to grow. It wasn't a sudden gathering. It was more like snow drifting into a hollow, or dust collecting in the corners of a still room. Tiny nudges. Soft momentum. But it added up. Over millions of years, these small clusters began to form larger ones. They weren't smooth or symmetrical. They weren't even stable. Some would fall apart. Others would be torn away by competing gravitational pulls. But a few held on. A few gathered just enough mass to keep going, to keep pulling, to keep building. All the while, the gas left behind by the first generation of stars was becoming more useful. Those early stars had exploded, sending out heavier elements, tiny amounts of carbon, oxygen, iron, into the surrounding clouds. These heavier atoms helped the gas cool more efficiently. And cooler gas collapses faster. So new stars began to form more quickly, and in greater numbers, inside the growing clusters. A second generation of light joined the first. Then a third. The clusters became brighter, denser, more active. Star formation was no longer rare. It was becoming the default. What had once been a silent drift was now a quiet storm, not loud, but steady, full of purpose. The universe had begun to build not just stars, but systems of stars. And within those systems, the idea of a galaxy was beginning to take shape. It's strange to think of a galaxy as something that grows like a city, but that's really what was happening. Small settlements of stars, scattered far apart, began to merge. Some collided head-on. Others brushed past and pulled at each other with long, delicate strands of gravity. These interactions weren't destructive in the way we might imagine. There were no star-on-star explosions. Space is vast, and even in a dense cluster, individual stars rarely touch. But their mutual gravity reshaped everything. Paths changed. Orbits stretched. Gas was stirred and compressed. New bursts of star formation lit up the darkness like fireworks over a silent plain. The stars themselves were like the citizens of this growing metropolis, and gravity was the unseen hand building roads and bridges between them. At this point in time, the universe was still young, less than 1 billion years old. But in cosmic terms, that was enough for real structure to begin emerging. Some of the growing clusters began to show hints of rotation. They weren't spinning fast, but they were spinning just enough for their shape to start changing. Instead of a random ball of stars, some began to flatten into disks. Others formed dense central bulges. None of it was tidy. There were no patterns yet. No spirals. No symmetry. But the transformation was undeniable. What had once been just points of light in the void were becoming something more, something connected. Something lasting. Even now, when we look deep into the universe with our most powerful telescopes, we can sometimes catch glimpses of this moment. We see faint, blurry patches of light from galaxies in the early stages of assembly, chaotic, uneven, but unmistakably real. Their light has traveled for more than 13 billion years, across an expanding universe, through dust and gas and gravity, just to arrive here, into our telescopes, onto our screens, and into our imaginations. And when we look at them, what we're really seeing is the first time the universe began to gather its stars into families. We're witnessing the moment the cosmos took its first architectural steps, not just building stars, but arranging them into neighborhoods, towns, and eventually, cities of light. And so, from scattered clusters and gentle gravity, the first whispers of galaxies were born, quietly, patiently, without blueprints or boundaries. Just stars, drawn to stars, pulled by forces older than memory. It didn't happen quickly, it didn't happen cleanly, but it happened, and the universe, once a quiet sea of individual lights, had begun to organize. The first steps toward galaxies were already in motion. In the young universe, even as galaxies were beginning to form, things were anything but peaceful. While gravity gently pulled stars together and shaped them into the early outlines of what would become galaxies, that same force also brought about something far less graceful: collisions. Not the explosive kind that break things apart in a single flash, but the slow-motion, inevitable kind. Picture two clouds drifting toward each other for millions of years, drawn by a shared tug they can't resist. Eventually, they meet, not with violence, but with momentum. That was what galaxy formation looked like in the beginning, a dance of attractions and impacts, shaping the cosmos through chaotic encounters. Back then, space was smaller, more compact. Galaxies, or rather, proto-galaxies, were closer together. The cosmic web was still tightening its strands, and regions dense in gas and stars became even denser as gravity pulled everything inward. As a result, collisions were common. Two star clusters drifting nearby would eventually begin to feel each other's pull. Slowly, across hundreds of millions of years, they would spiral in, their shapes warping, their gas clouds colliding, their stars slinging past each other in gravitational whirlpools. From a distance, it would have looked majestic, bright patches of light stretching toward one another, merging, blending, and reshaping themselves in a silent, cosmic ballet. It's tempting to think of these events as destructive, but in reality, they were incredibly creative. When galaxies, or clusters of stars and gas, collided, their stars didn't smash into each other like cars on a highway. Stars are far too small and too far apart for that. Even during a galactic merger, most stars pass right by one another, like two flocks of birds flying through the same patch of sky. What really collided was the gas, the vast, invisible clouds of hydrogen and helium that filled the spaces between the stars. When these gas clouds crashed, they compressed. And compressed gas is exactly what gravity needs to create new stars. These collisions didn't just distort galaxies, they gave birth to countless new suns. Astronomers have a name for this process. They call it a starburst, because that's exactly what it is, a sudden burst of star formation triggered by gravitational upheaval. A single collision could trigger tens of thousands, even millions of new stars to form. The sky in those regions would have lit up with brand new light, not all at once, but over time, as one new star after another blinked on like lanterns in a deepening dusk. In a way, the universe was experiencing its first round of dramatic urban growth, cities of stars expanding overnight because two neighborhoods collided. But these mergers weren't neat. They were messy. When one structure slammed into another, it didn't always result in harmony. Sometimes, stars were flung out into the dark, stripped from their clusters by gravitational tides. Other times, the shapes of galaxies became tangled, lopsided, or pulled into long trailing arms, streamers of stars and gas stretching out like ribbons caught in the wind. Some of the most beautiful galactic forms we see today, like tidal tails and ring galaxies, are the lasting scars of ancient collisions. And of course, not all galaxies fared equally. Some, the more massive ones, grew stronger from these interactions. They swallowed smaller neighbors, absorbed their gas, and used it to form even more stars. Over time, these became the giants, the grand spirals and massive ellipticals that dominate galactic centers today. Other galaxies weren't so lucky. They were torn apart, their stars scattered, their identities lost. They became streams of light drifting between larger galaxies, whispers of former structure, now repurposed by the gravitational currents of the cosmos. These chaotic mergers happened over and over again, not just in the early universe, but continuing even now. Our own Milky Way has swallowed many smaller galaxies over the course of its life. Some of those stars still orbit through our sky, invisible to the naked eye but traceable by telescopes. And the dance isn't done. In about 4 billion years, we'll merge with our closest large neighbor, the Andromeda Galaxy, and become something entirely new. A different shape. A different structure. A different story. Back then, though, during these early chaotic times, the universe was full of such encounters. Collisions were not exceptions. They were the rule. And from that rule came variety. Some galaxies settled into stable, rotating disks, the beginning of spirals. Others, pummeled again and again by mergers, became rounded and featureless, the first ellipticals. Some never formed a clear shape at all, becoming irregular, patchy, and unpredictable. Each outcome depended on the timing, the angle, the amount of gas, and the gravitational tug of nearby companions. And so, in this era of cosmic collisions, the universe began shaping its character, not through silence, but through chaos. It was a time of growth through disruption, of beauty born from imbalance. It's easy to forget, when looking at a beautiful spiral galaxy today, that its form was likely carved through moments of disorder. But that's how the cosmos works. From tension, it finds harmony. From collision, it creates structure. From a storm of scattered light, it begins to tell a story. After all the collisions, the chaos, the bursts of star formation, and the gravitational pushing and pulling that shaped the early cosmos, something remarkable began to happen. Slowly, the universe started to calm down. Not everywhere, and not entirely, but in enough places that patterns began to emerge. Some of the once chaotic clumps of stars and gas started to find their balance. They began to spin, and in that spin, they found stability. It was subtle at first, a gentle rotation, a slight flattening, a moment of pause in a universe that had only ever known motion. But over millions of years, this delicate movement transformed irregular, unstable clouds into something far more graceful. These spinning clumps became the earliest versions of disk galaxies. At the center, mass accumulated, pulling more stars inward, forming a dense core. Around that core, the rotation flattened the surrounding stars and gas into a wide, thin plane, like a pancake made of starlight. This wasn't a conscious design. There were no architects, no blueprints. Just gravity, inertia, and time, working together to smooth out the mess. Over time, density waves rippled through the spinning disks, like patterns in a vinyl record, compressing gas along their paths and igniting waves of star formation. These ripples became the arms of spiral galaxies, and just like that, beauty began to bloom in the dark. Spiral arms are not solid structures. They're not held in place by invisible threads. Instead, they are more like traffic jams in space. Stars and gas move in and out of them constantly, but the pattern, the wave, persists. Inside those arms, stars are born in brilliant clusters. Young, hot, and blue, they light up the spirals like holiday lights on a slowly turning wheel. These galaxies were dynamic, alive with energy, with stars being born and dying in steady rhythm. It was a far cry from the lumpy, shapeless blobs that came before. But not every galaxy found this elegance. Some had too much mass, or too many collisions. Their rotation wasn't smooth. Their shape wasn't clean. Instead of flattening into spirals, they puffed up, becoming elliptical galaxies, rounded collections of stars that orbited in all directions, like bees around a hive. These ellipticals were older, redder, and quieter. They had burned through much of their gas, leaving behind stars that glowed more softly and formed less frequently. While spirals were active cities filled with young light, ellipticals became like ancient capitals, majestic, massive, but slow to change. And then there were the ones that never quite figured it out, the irregular galaxies. Twisted, lopsided, and chaotic, these galaxies refused to conform to any single shape. Some were disrupted by gravitational tugs from larger neighbors. Others were simply young and hadn't yet found their rhythm. But despite their lack of symmetry, these irregulars were often rich in gas and full of potential, bursting with new stars and raw energy. They were the wild cards of the universe, unpredictable, messy, and, in their own way, beautiful. Even now, billions of years later, galaxies continue to shift and evolve. Spirals can become ellipticals if they collide with enough force. Irregulars can mature into more stable forms if given time and space. Nothing in the universe stands still. But in that early epoch, as the dust began to settle and the wild storms of matter gave way to motion and form, the great transformation had begun. From chaos came shape. From clumps came disks. From collisions came curves. The cosmos had started to sculpt not just stars, but structure. And when we look up at the sky today and see the elegant spirals of Andromeda or the delicate arms of our own Milky Way, we're seeing the outcome of billions of years of this natural choreography. We're looking at patterns forged not by design, but by motion. By gravity, by time. A spiral galaxy is not a frozen thing. It is a slow dance of stars and gas, a memory of collisions, a promise of change. And it all began when the universe, still young and messy, began to breathe more calmly, and found its balance. As galaxies began to take shape, to spin and settle and find their form, it might have seemed like they were simply floating alone in space, scattered islands of stars, each building its own quiet story. But the truth is, they were never truly isolated. Even from the earliest moments, something deeper had been guiding their placement, an invisible framework laid down during the inflationary burst after the Big Bang. That framework, woven from dark matter and tiny fluctuations in density, became the cosmic web, a vast, interconnected structure that would determine where galaxies could form, how they would gather, and what shape the universe would ultimately take. The cosmic web isn't something we can see directly, at least not with our eyes, but it's there. Stretching across billions of light-years, it forms a three-dimensional lattice of matter, where galaxies collect along long filaments and cluster at their intersections. In between those filaments lie enormous voids, immense stretches of near-empty space, where few galaxies ever form. It's a structure both massive and delicate, something like a sponge or a cobweb, scaled up to cosmic proportions. And just like the nerves in a body or the branches in a tree, it channels motion, connection, and growth across the entire universe. This web was shaped by dark matter, a mysterious substance that doesn't emit or absorb light, that can't be seen, touched, or measured directly, but whose gravitational influence is undeniable. Dark matter clumped first, guided by the initial ripples from inflation, forming a kind of scaffold that regular matter, the stuff we're made of, then followed. Hydrogen and helium gas streamed along these invisible pathways, drawn in by gravity, and wherever enough material accumulated, galaxies began to form. It was dark matter that decided where the great cities of stars would rise, and it continues to hold them in place even now, like the steel beams inside a skyscraper you can't see from the street. When we map the positions of galaxies across the sky, we don't find randomness. We find patterns, lines, nodes, clusters, and threads, all echoing the invisible skeleton beneath them. The brightest and largest galaxies often lie at the nodes, the intersection points where filaments of dark matter cross. These places are full of motion, full of gravity, full of change. Galaxies in these hubs grow quickly, merging with others, pulling in new material, evolving rapidly. Meanwhile, galaxies on the edges of filaments live quieter lives, less disturbed, more stable, slower to change. And in the vast dark voids between, there is almost nothing. A galaxy forming there would be like a tree growing in the middle of a desert, possible, but unlikely. Even the way galaxies move is shaped by this web. Their motions aren't random. They're being tugged by the filaments they sit on, slowly flowing toward the larger clusters and nodes. It's as though the universe itself is breathing, drawing material inward along its ancient veins. Over billions of years, this has created vast structures, galaxy clusters, superclusters, and walls of galaxies that span hundreds of millions of light-years. One of the largest of these is the Laniakea supercluster, the cosmic region our own Milky Way belongs to, a flowing, gravitationally connected region filled with tens of thousands of galaxies, all gently drifting toward a shared center. This cosmic web continues to shape the universe today. It's not frozen, it's evolving. As galaxies burn through their gas, as dark energy stretches space ever further, the filaments grow thinner, the voids grow darker, and the clusters grow denser. But the pattern remains. The architecture is still there. And from our small vantage point within one galaxy, inside one filament, in one corner of one supercluster, we can see just enough to recognize it, to understand that we are part of something vast, elegant, and ancient. The cosmic web reminds us that galaxies are not just individual wonders. They are parts of a much greater whole, interconnected, shaped by invisible hands, drawn into relationships across unimaginable distances. The universe is not a random scattering of stars. It is a structure, living, shifting, stretching, and everything we see, from the smallest dwarf galaxy to the brightest supernova, is playing out along its threads. By now, the universe had come a long way from its chaotic beginnings. From a seething soup of energy and particles, to the birth of the first stars, to the slow, tangled formation of galaxies, the cosmos had finally begun to take shape. The darkness had been pierced. The silence had been broken. And as galaxies aligned along the threads of the cosmic web, something new began to happen, something even more complex, more organized, and more magnificent. Galaxies were no longer evolving alone. They were starting to form communities. They were building the first cosmic cities. It began quietly, as most grand things do. Galaxies drifted closer together along the filaments of dark matter that had been pulling them since the dawn of structure. They gathered at the intersections, in the gravitational wells where the cosmic web converged. And when they arrived, they didn't just sit side by side. They orbited one another, interacted, merged, and shaped each other's fates. These weren't random meetings. They were the natural outcome of billions of years of cosmic flow. Galaxies didn't simply end up near each other. They were drawn together, pieces of a puzzle coming into place, guided by invisible forces older than time itself. These growing clusters of galaxies became the first galactic neighborhoods. Dozens, sometimes hundreds of galaxies, all held together by their shared gravity, moving in complex orbits like planets around a star. Some clusters were dense and busy, full of interaction and light. Others were more sparse, quieter, spread across the outskirts of the web. But each one was a kind of cosmic metropolis, a region where galaxies could influence one another, collide, grow, and evolve faster than they could in isolation. And the interactions continued. Smaller galaxies were pulled into larger ones, contributing their stars, their gas, their black holes. Larger galaxies grew fat on mergers, becoming sprawling giants with millions, even trillions, of stars. Central black holes grew as well, feeding on the inflow of gas stirred up by galactic encounters. And when they fed, they didn't do so quietly. They released enormous jets of energy, sometimes brighter than the galaxies themselves, sculpting the environment around them and slowing the formation of new stars. These were not just galaxies anymore. They were ecosystems, dynamic, self-regulating, and deeply interconnected. Over time, some regions of space became particularly rich in structure. Massive galaxy clusters formed, and those clusters began to connect with others, forming superclusters, immense, gravitationally bound regions filled with thousands of galaxies, all drifting together through the void. These were the largest structures the universe would ever build, the ultimate expression of cosmic architecture. They didn't form quickly. They took billions of years, but once in place, they became the backbone of the modern universe. Even our own home, the Milky Way, is not alone. We are part of a small group of galaxies known as the Local Group, which includes Andromeda, the Triangulum Galaxy, and dozens of smaller companions. Together, we drift through space toward the Virgo cluster, which itself is part of the even larger Laniakea supercluster. From our position inside one spiral arm of one galaxy, we may feel isolated. But we are deeply embedded in a web of relationships that spans hundreds of millions of light-years. Our galaxy has neighbors. It has history, and it has a future that is tied to everything around it. What began as scattered points of light had become organized. Not just into galaxies, but into clusters, groups, superclusters, entire cosmic cities connected by threads of dark matter and shared motion. These structures are not static. They evolve, shift, grow. They are built not from stone and steel, but from stars and gravity. They are cities without borders, without streets, without limits, and yet they shape the destiny of every star, every planet, every atom within them. So here we are, near the end of this chapter in the universe's story. From the first sparks of starlight to the great cosmic web to the rise of galactic communities, the universe has become not just filled with things, but organized in meaning. It has structure. It has pattern. And it has history. Galaxies no longer shine in solitude. They shine together, parts of something greater, something vast, something still unfolding. The cosmic cities are alive, and we are lucky enough to be part of one. Now that galaxies had formed and gathered, now that they were no longer scattered lights drifting alone in the dark but members of larger cosmic neighborhoods, a new question began to emerge. Why do galaxies look the way they do? Why do some spin in perfect spirals, arms stretched wide like dancers in mid-turn, while others form smooth, rounded ellipses or irregular, chaotic shapes that seem to defy any pattern at all? These shapes aren't just visual curiosities. They are reflections of each galaxy's story, of how it was formed, what it has survived, how much gas it has left, and how many stars it continues to create. Just as the lines on a face tell the story of a life lived, the shape of a galaxy tells the history of matter, motion, and time. Let's begin with the spirals, the showpieces of the night sky. Spiral galaxies are among the most beautiful structures in the universe. They're the ones that appear in posters and documentaries, with glowing arms curving around bright central bulges. Our own Milky Way is one of them. Spirals tend to form when a galaxy has enough angular momentum, that is, when its gas and stars are rotating in a roughly consistent direction. That spin causes the galaxy to flatten into a disk, like pizza dough tossed into the air. Over time, density waves ripple through that disk, compressing gas and triggering star formation as they go. These waves aren't made of stars themselves, they're patterns, like traffic jams that move through a city even as individual cars come and go. The result is a spiral structure that endures, even as its stars move in and out. And because spiral arms are rich in gas and dust, they are full of young, hot, blue stars, which shine brightly and give spirals their iconic, glittering appearance. But not every galaxy is so elegant. Some are more subdued, more settled, more spherical. These are the elliptical galaxies, large, rounded clouds of stars that have little gas left and rarely form new stars. Ellipticals often form through mergers, two or more galaxies crashing together and scrambling the orbits of their stars until no clear direction of rotation remains. What's left is a kind of stellar cloud, where stars move in random paths, like bees buzzing around a hive. These galaxies are often home to older, redder stars, the remnants of a once busy but now quieter history. If spiral galaxies are like vibrant, growing cities, full of lights and noise and construction, then ellipticals are like ancient stone capitals, majestic, still, and no longer expanding. Then there are the irregulars, galaxies that don't seem to follow any particular pattern at all. Some are young and haven't yet settled into a shape. Others are victims of disruption, tugged and twisted by nearby neighbors or shaped by past collisions that left them bent out of form. They might appear as jumbled collections of stars, like sketches half erased, or as asymmetrical blobs of light that drift at odd angles across the sky. And yet, many irregular galaxies are bursting with star formation, full of energy and gas, forming new stars at a rapid pace. They are chaotic, yes, but also full of potential. They remind us that not all beauty is orderly. Sometimes, it's in the mess that the universe shines brightest. Of course, many galaxies fall somewhere in between. There are spirals with large central bulges, or ellipticals that show hints of rotation, or hybrids that seem to change category depending on the angle from which we observe them. Galaxy morphology, the classification of shape, is more of a spectrum than a set of boxes. Astronomers try their best to fit them into categories, but the universe doesn't always cooperate. And that's okay. Because what matters most is that every galaxy's shape tells a story, not just of what it looks like now, but of everything it has been through. The shape of a galaxy is a record of gravity and time, of motion and memory. When we look at a spiral galaxy billions of light years away, we're seeing it not as it is now, but as it was long ago, its light having traveled for eons to reach us. That spiral, frozen in space, is really a moment in motion, a snapshot of something constantly changing. Galaxies twist and evolve. Spirals can become ellipticals after a collision. Irregulars can settle into spirals with time. Nothing in the cosmos is fixed, not even these great cities of stars. And yet, in their current forms, they offer us a glimpse into the forces that shape them. So when you see a galaxy, whether it's a perfect spiral with blue arms, a glowing elliptical orb, or a tangle of irregular light, you're not just seeing a beautiful image. You're seeing the outcome of billions of years of cosmic evolution, of collisions and mergers, of star births and deaths, of gas pulled in and blown away. You're seeing the memory of motion, the echo of gravity, the shape of time itself. And perhaps, most beautifully of all, you're seeing a reflection of the universe's ability to take chaos, and turn it into art. Among all the galaxies scattered across the cosmos, spiral galaxies stand out as some of the most visually striking, instantly recognizable, and perhaps most poetically alive. With their swirling arms, glowing cores, and sweeping curves, they seem almost like frozen whirlpools, snapshots of graceful motion that stretch across hundreds of thousands of light years. But their beauty is not just surface level. The spiral form is a direct result of movement, of the quiet, persistent rotation that begins when a galaxy is young and carries through for billions of years. It's a structure born of balance, a dance between gravity, inertia, and the gentle friction of gas and dust. To understand spiral galaxies is to understand how motion sculpts matter, and how even in the cold vacuum of space, momentum gives rise to brilliance. At the heart of a spiral galaxy lies its bulge, a bright, dense sphere of older stars packed close together, orbiting in all directions like a glowing hub. Surrounding this bulge is the disk, flat, wide, and rotating. This disk is where the spiral arms live. It may look like the whole galaxy is turning in unison, like a spinning record, but it isn't. The stars near the center orbit faster than those farther out, and over time, this differential rotation should smear the arms out, erasing them. And yet, the arms remain. They persist not as solid structures, but as patterns, regions of higher density that move through the disk like waves in water. As these waves pass through clouds of gas, they compress them, triggering star formation. New stars, bright and blue and short-lived, illuminate the arms, making them visible. Older stars fade and drift out, replaced by new ones. The arms are never made of the same stars twice, but the shape remains. It is a living structure, made possible by the constant birth and death of stars. Gas is key to the spiral's survival. Without fresh gas, the arms would go dim. But as long as there's gas to compress, new stars will continue to form. These stars are often born in clusters, in regions called stellar nurseries, where the gas is especially dense. In images from telescopes like Hubble or James Webb, these nurseries appear as pinkish clouds or brilliant knots of blue light, peppered throughout the spiral arms. They're the cradles of starlight, and they give spirals their sparkling, dynamic look. It's not just beauty for beauty's sake, it's the mark of a galaxy still alive, still building, still growing. Our own Milky Way is one of these spiral galaxies. From our vantage point inside it, we can't see the whole spiral form directly. It's like trying to photograph your own house from the inside, but we've mapped it through careful observation of stars, gas, and radio waves. We know it has at least 4 major arms, winding around a bright central bulge and a mysterious bar of stars that stretches across its core. These arms are not static. They are rotating, slowly but surely, taking hundreds of millions of years to complete a single turn. And as they turn, they shape the future of everything inside them, including us. Spiral galaxies also tell us about the larger forces at play. Their rotation curves, how fast stars orbit at different distances from the center, don't follow what we'd expect if all their mass came from the stars and gas we can see. Instead, stars farther out orbit much faster than they should. This was one of the first big clues that something invisible was shaping galaxies from within, something we now call dark matter. Without it, the spirals would fly apart. But with it, they hold together, stable and magnificent, their shapes preserved over billions of years. Not all spirals are alike. Some are tight and smooth, with thin arms that wind closely around the core. Others are loose and open, their arms flung wide like ribbons in the wind. Some have large central bulges and thick disks. Others are more delicate, with less dust and more symmetry. The Hubble sequence, a system astronomers use to classify galaxies, divides spirals into categories based on how tight their arms are, how big their bulges are, and whether they have a central bar. But again, these categories are only snapshots. Galaxies evolve. A spiral can grow thicker, slower, redder. It can become distorted by a collision or fade into an elliptical over time. Its shape is never permanent. It is only ever current. And yet, despite their vulnerability, spirals are everywhere. They make up the majority of visible galaxies in the nearby universe, not because they're the most stable, but because they're among the most active. As long as a spiral galaxy has gas, as long as it's rotating, as long as it's not disturbed too violently, it will continue creating stars and maintaining its structure. It will keep glowing, keep spinning, keep dancing in space. When we see a spiral galaxy through a telescope, whether it's the graceful arms of Andromeda, the elegant sweep of the Whirlpool galaxy, or the tightly wound beauty of Messier 81, what we're really seeing is the harmony of physics. We're seeing what happens when gravity, gas, and motion come together over billions of years. We're seeing a story not written in words but in rotation. And perhaps most humbling of all, we're seeing our own home from afar, a structure so vast it defies imagination, and yet so delicately shaped that it reminds us, the universe is not just cold and vast. It is also patient, persistent, and unimaginably beautiful. Not every galaxy spins in elegant spirals or dazzles with newborn stars. Some galaxies have already lived out their most active years. They've burned brightly, collided, merged, and grown massive, and now, they shine more quietly, like old cities whose towers still stand tall, even if their lights have dimmed. These are the elliptical galaxies, the ancient giants of the cosmos. They may not catch the eye the way spirals do, but they hold a kind of quiet authority, a cosmic wisdom earned through time. Their shapes are smooth, rounded, and soft-edged, with no arms, no disks, no dramatic curves, just a dense, glowing sphere that fades gently into the dark. But what seems simple on the outside hides a deep and intricate story within. Inside elliptical galaxies, stars move in every direction, tracing out chaotic paths. Unlike spiral galaxies, where most stars follow a consistent, ordered orbit around the center, elliptical galaxies have no preferred direction. Stars buzz like bees around a hive, not around a wheel. The result is a galaxy without symmetry, without rotation, but with immense gravitational stability. The stars inside them are mostly old, red, cool, and long-lived. These galaxies rarely form new stars, because they've used up or lost most of their cold gas, the raw material for starbirth. That gives them a golden hue, soft and subdued. They glow not with youth, but with age. They are the elders of the universe. How do galaxies become elliptical? Often, through dramatic collisions. When two spiral galaxies merge, their stars are flung into new orbits, their disks disrupted, their rotation lost. The aftermath is a rounded structure, a kind of stellar cloud, where order gives way to equilibrium. And the more collisions a galaxy experiences, the more likely it is to become an elliptical. Over time, as galaxies in crowded environments like clusters bump into one another again and again, spirals are transformed, their gas is stripped, and the grand structures of their youth dissolve into calm. What remains is a galaxy that remembers everything, every merger, every flare, every moment of chaos, but no longer needs to relive it. Elliptical galaxies are often home to some of the largest black holes we've ever observed. Though invisible to the eye, these black holes anchor the centers of these galaxies with masses millions or even billions of times greater than our Sun. And while they may lie dormant for long stretches, when they feed, they can unleash jets of energy that stretch for thousands of light-years, affecting the gas around them and even regulating the growth of their host galaxy. These black holes are like sleeping giants, silent most of the time, but powerful enough to shape the destiny of their surroundings. It is through them that ellipticals remind us, just because something is quiet, doesn't mean it is inactive. Even in their stillness, elliptical galaxies are not static. Stars inside them continue to orbit. Black holes occasionally stir. And sometimes, a small companion galaxy may wander too close, triggering a ripple, a shift, a moment of new motion. But on the whole, these are galaxies in the twilight of their activity. They are places of stability, not growth. Of memory, not invention. And that is a kind of beauty all its own. So as we close this chapter on galaxy morphology, on the shapes that define the great cities of stars, we see a full spectrum of cosmic expression. We've seen the spirals, vibrant and rotating, alive with starbirth and motion. We've seen the ellipticals, grand and settled, shaped by ancient violence and long-term quiet. And we've touched on the irregulars, those galaxies that refuse to fit into any category, full of wild energy and potential. Each shape tells a story. Not just of what the galaxy looks like now, but of everything it has experienced. Spirals are stories still being written. Ellipticals are libraries of memory. And together, they form a universe not only filled with stars, but full of history, emotion, and identity. Perhaps, the next time you look at a galaxy in a photograph, whether it's an elegant spiral or a gentle sphere of golden light, you'll see more than just shape. You'll see a life. A path. A process that took billions of years to unfold. You'll see a cosmic city, not frozen, but alive in slow motion. And you'll remember that everything, even the stars themselves, has a story to tell. And so, as we step back from this gallery of galaxies, spirals, ellipticals, irregulars, we begin to understand that shape is never just about appearance. It's about history. It's about movement, pressure, collision, silence, and time. A spiral is not simply a disk, it is the memory of angular momentum preserved across billions of years. An elliptical is not merely a glowing ball of stars, it is a graveyard of ancient collisions, quiet but massive. And even the irregulars, with their chaotic forms, are the raw sketches of a universe still creating, still experimenting, still alive with energy. Together, these forms reveal not just the diversity of the cosmos, but its creativity, its ability to take the same basic ingredients and tell wildly different stories through structure alone. But these stories are never finished. No galaxy remains the same forever. Over time, spirals can merge and fade, ellipticals can stir, irregulars can find shape, and new galaxies can be born from clouds that have not yet settled into stars. Morphology, then, is not destiny, it is a moment. A frame pulled from a cosmic film that stretches endlessly in both directions. And as we now leave behind the question of what galaxies look like, we turn to a new one: how do they change? How do these cities of stars grow, age, and transform across cosmic time? Because if there's one lesson the universe keeps teaching, it's this: nothing stays still forever.